Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Ago, and I was asked if I'd be interested, given on my topic of my talk on decision making under uncertainty, if I'd be interested in being a subject in their study, take out an hour instead of chatting with somebody at Caltech to sit in an MRI tube and be imaged while answering lottery questions, lottery challenges, and I did that, and I enjoyed the experience, and I hope my brain is still intact from all that hammering. But as part of my souvenirs, I got some pictures of some subtraction photos of how I looked under well-defined lotteries versus lotteries in which I had poor information about the outcomes. So in that Ming's team, right, that was really what was going on. So Ming and his team published a science article. It appeared in December of 2005, and it's a very interesting read on a direction that's growing in interest in science and in the lay press, neuroeconomics, and Ming also is interested in more traditional e-commerce topics as well. So today he'll be talking about the Ellsberg Paradox and the neural foundations of decision-making under uncertainty, reviewing some of the work that I got a little peek at inside and out. And he's been working with his advisor, Colin Kammerer, quite closely on this, and Colin just had a baby, what, yesterday?
No, Friday.
Friday.
Yeah.
People who know Colin, so he couldn't be here today. So, Ming.
Okay. Okay, hopefully this is working. Okay, so thanks Eric for inviting me. So this topic is on the neural foundations of decision-making under uncertainty. So this is as Eric said, this is a new and quite burgeoning field in economics and neuroscience today. So in particular, this topic, I'm going to be talking about the more empirical parts of neuroeconomics. And here I'm going to combine evidence from, well, at least two and also at least three different sources. So neuroimaging, which is the most widely at least cited part, so brain imaging, so scanning in fMRI or PET, in this case it's going to be fMRI. And also lesion patients, these are people with brain damage of certain ways. I'll get to why we use people with brain damage later on. And also traditional behavioral experiments. So this is what's been done in economics for the past 40, 50 years. And so the topic is going to be on decision theory. So there are two goals of decision theory. So one is prescriptive. So how should people weigh and combine likelihoods and outcomes to make decisions, right? So there's another one that's more descriptive, and this is how do people, or not just people, but how do organisms weigh and combine likelihoods and outcomes? And this is, of course, a fundamental activity in everyday life. So things such as risky investments, which includes stocks and who you should marry, which college you should go to very kind of macro risks, terrorism, global warming, and to even questions like, which operating system should I use?
So you have a Macintosh up there.
Yeah. So I can expect to not leave this building. Okay. So the dominant strand in economics and in the decision sciences is subjective expected utility theory. And there, people are assumed to, people's probability assessments are assumed to be subjective. So I can hold whatever whatever probabilities I can about the world, so long as they satisfy certain axioms. So the completeness, transitivity, continuity, independence, some are more technical than others. In particular, later in this talk, I'm going to focus on one of them that's inspired a lot of controversy, which is the independence axiom. So I'll get into that more later. Okay? Mm-hmm.
You say that as a given, a base of an axiom. I think none of this, I'm not sure what axioms exactly are, but none of them is obvious.
It's, some certain ones are technical, like completeness. Completeness just says you have preference rankings over all outcomes. And there it's it's basically a technical, you need that technical assumption to be able to make choices under basically, I mean, you can restrict that, say, well, we only can make choices under certain domains. But some are more technical than others. But independence is clearly, which I'll get into later, is clearly one of the most.
Don't answer my question. Is it accepted? What is the evidence that our subjective probabilities satisfy these axioms?
So a lot of these are. So some of these are just intuition. So that intuitively we should satisfy these. Some of these are from arguments about arbitrage. So like no arbitrage conditions. That if you, and I'll get into that later too. That if you don't satisfy these axioms, then we can basically take advantage of your inconsistencies in your choices and extract rent from you, extract money from you by constructing series of gambles. And so. Oh no, this is So this is under the theory. So under SEU, this is normative. Yeah. Under SEU, they obey the axioms. Yeah.
So you don't claim that.
Right. No, this is what SEU says. Yeah. This is what everything that's under SEU. Yeah.
Could you just one brief sentence each say what transitivity and continuity are?
Okay. So continuity says that you can basically have it's completeness, I really want to. Transitivity is that if I prefer A to B and B to C, then I prefer A to C. Okay? And independence I'll get into. Continuity is if I prefer A to B, then I can mix. If I can prefer A to B to C, then there's some mixture of A and C that I can prefer B. That's different between B. So I mean some of these are more technical than others, like I said. Okay, so if we satisfy these axioms, then we can infer probability assessments from people's behavior, probability assessments and preferences.
But is it a straw man, or there are serious people who actually?
Oh no, this is dominant. I mean, this is definitely not a straw man. Yeah, there are problems with SEU, and that's partly what we're gonna go into. But there are strong kind of normative implications to come out of SEU, and also there are pretty good descriptive. This theory is pretty good descriptively. At least describing people's actual behavior. Not perfect, and that's what we're going to get into. Okay, so this is one of the big normative criteria for subjective expected utility. It says otherwise behavior inconsistent, and we can arbitrage it. So we can construct series of gambles such that I give you a gamble, and then you will lose because you violate one of these axioms. You will lose money with probability 1. Okay, so I can create these situations where you will always lose money. And the thinking goes, people should not be like this, and that if there are people who violate these axioms, then they're going to be arbitraged out of existence. So that's very close to the kind of efficient market hypothesis that floats around in finance. That if people violate these behavior, then they'll be evolutionarily they won't be selected for. Go ahead.
Given how much money various lotteries make, it is a good assumption. I mean, the state lottery makes money with probability 1.
Right. Yeah.
Enough people will gamble.
Yeah.
I'm really glad to have Phil Newman today.
No, that's definitely, yeah. Okay, so the independence axiom is the following. So if I prefer X to Y, so these are lotteries, say, these are X, but say these are lotteries. If I prefer X to Y, then then if I add another Z to both X and Y, then my preference rankings should remain the same, right? So this is independence. So this is called independence because Z is independent of whether I choose X and Y. I'll get Z no matter what. So Z, the addition of Z, shouldn't affect my choice rankings over X and Y. Okay? And so this seems very, intuitively this seems, unobjectionable, right? Oops. Why does this work? Okay. So similar criteria is a sure thing principle. And one thing to note is that expected utility is linear in probabilities, right? So P of X, so if I multiply X and Y by P, the same rankings should be obtained. Okay, so there are a number of empirical challenges to the independence axiom, and one of the earliest and most kind of intuitive and long-standing is the Ellsberg paradox. Okay, so what is the Ellsberg paradox? So in the Ellsberg paradox, you're given two different urns. So there's an urn 1. So in this urn, you're told that there are 5 blues and 5 reds. Okay? And then I ask you to choose between a bet on blue or red. So I ask you, for $10, which color would you choose? And most people, in this case, it's quite transparent. Most people are indifferent between betting on red versus blue, because there are 5 of each, right? And there are 10 balls total. Okay, so now I'll give you another urn 2. And now I tell you there are only reds and blues in this urn, except I'm not going to tell you the composition of the urn. So, but you know that there are only 10. Okay, so the probability distributions are limited by this information. So there could be 0, 1, etc., or all the way to 10 reds and 10 minus X blues. In this case, if I give you the gambles on blues and reds, most people are also indifferent between the blues and red, because I have no more information to bias me for one than the other, so I'm going to be indifferent. Okay, so the paradox arises when you combine the urns. So now I give you urn 1 and urn 2, and I ask you, which color would you rather bet on, or which urn would you rather bet on? The red in urn 1 or the red in urn 2? Alternatively, the red in urn 1, the blue in urn 2, etc., etc. Okay, and now most people prefer betting on urn 1 over urn 2 over all the acts, and so that's where the paradox arises, right? Because
I think it depends on my risk, right? A tolerance. If I'm very risky, I'm happy to.
No, because your risk tolerance should be exactly the same between urn 1 and urn 2. Right? So I'll give you a $10 bet. So risk aversion in economics is the curvature of the utility function. So, and in this case, it's exactly the same. The outcome, I give you $10 for if it's a draw out of red in urn 1, $10 for red in urn 2. So there, the outcomes are exactly the same. So there shouldn't be. So the risk aversion is controlled for. Mm-hmm.
If I may, it seems to me it's a pseudo-paradox.
Mm-hmm.
It's a rational decision to choose urn 1,
Mm-hmm.
and you economize something, and something is decision making.
Mm-hmm.
So suppose I chose urn 1.
Mm-hmm.
So my expected gain is $5.
Mm-hmm.
And that's the only decision I make.
All right.
The paradox is that you presume that I first make a decision about the probability in urn 2.
Right.
And then make another decision.
Mm-hmm. Yeah.
So there are 2 decisions.
Yeah, there are 2. Okay, so there are lots of theories about exactly what you said, that this is actually people make some inference about the probability, and then they make some inference about the expected utility. And
I want to say it's not about independence. It's about something else, about number of decisions.
So it's about, it definitely violates independence. Whether it's about independence or not is another question. It's just an axiom that they violate. So part of it's about whether the axiom is plausible or not. But in here, there's lots of different explanations for. Part of the reason for the study is that there are lots of different explanations for why people prefer urn 1 to urn 2, right? So you could be that they're minimizing on say thought, on the cost of thought, and thought is costly, or they can just be pessimistic. They can be pessimistic about urn 2, about the distribution of urn 2, because here you have a set. And so one of the prominent theories in economics is that when you have sets of distributions, what people do is people pick the worst. People minimize or maximize over the minimum or the worst case outcome in this case. And these are all kind of normatively, these all seem plausible, and we don't really, it's very difficult to design behavioral experiments to distinguish between them. So that's. But that's just what you say is definitely one of the sources that people apply to ambiguity aversion, but it's certainly not the only one. There are lots of other ways you can produce this type of behavior, lots of different models.
So the issue there is that for urn 2, you don't know the composition of blue and red.
Right, but you know that
there's more risk over there.
There's not more risk because there are only 10 balls, right? So if you think that there are 2 reds and 8 blues, then you should bet on blue.
So we don't know.
So you don't know, and by you being indifferent between the red and the blues in urn 2, what you're saying is they're equally likely. And hold on, let me just get to the next slide, just to okay. And so the problem is that you're saying what you're saying in here by preferring earn 1 to earn 2, you're saying that the probability of red for earn 2 from earn 2 is less than 50%, is less than 0.5. Probability of blue is less than 0.5. You're shaking your head, but this is all produced by SCU, and but it's also more general. And the probability of blue plus the probability of red has to be equal to 1, right? Because that's all you're told that information. There are only blues and reds in this term. And more generally, so this violates some basic principles of probabilities, that your beliefs cannot be represented by any probability distribution. All right, so that's the, okay, and question?
Yes. Maybe the issue is people already believe there will be a next time. The war to end all wars ended in 1918. So if this repeats and repeats and repeats, I'm better off with a 50% chance than unknown chance.
No, actually, if it repeats, if the probabilities are stationary and you get to choose sample over time, you should prefer earn 2. Because if earn 2, if you have, say, a uniform, if you have any distribution other than a dogmatic prior on 50-50, then you should prefer earn 2, right? So if there are actually 8 blues and 2 reds, what you find out, then you should bet on blue. So over time, you can find out more information about the distribution, and you should actually prefer earn 2. But in the one-shot game, people seem to prefer earn 1. Yeah.
If my utility function is, I'm happy if I have at least $1,
Mm-hmm.
and I don't care about $2 or $0, and I'm unhappy if I get $0, does it remain there?
In this case, yes, because even in here, so say that you're betting over 10 blues and or $10 or $0, and in here it's also the same thing. It shouldn't matter whether you have a step function for utility function, because in here you're also looking at 0 or 10. I mean, you just have an expected value of $5. And here, what you're saying is, from your preferences, you're saying that you think the composition is 50-50.
So if I'm mentally thinking, all I care about is getting at least $1.
Mm-hmm.
And so the probability of not getting at least $1 and earn 1 is very, very small.
Oh, okay.
So I'm
Okay.
thinking earn
Right.
1 for all practical purposes
Yeah.
is a sure thing. That's happen.
So what you,
Still,
yeah. But you have to set that in terms of a set of priors. So you say that. So what you would have to make that argument work, you have to say there's a set of priors from 1 blue to 10 blues, and what I want to do is maximize the probability that I get at least $1, and that's very similar to the kind of min max or max min arguments out there. That what I want to do is maximize my probability of getting some worst case outcome. Right. But in terms of the decision theory, it's very simple that the two are identical from your behavior on the individual earns, and so they should be identical earns, but you're acting as if they're different. Yeah.
So you
The last question. Sorry, I have to go on.
Suppose you have such and such utility,
Mm-hmm.
and then you get the computation.
Mm.
But this supposition, I think, is a fallacy.
Mm-hmm.
Because you force me to come up with a utility function.
Mm.
I have no grounds to prefer any number of blues.
Mm-hmm.
So instead of trying to solve a very difficult problem of forming a utility function before doing anything, I can go for earn 1.
Mm.
I lose nothing. I don't have to solve difficult problem. So the fallacy only arises if you force it. When people see two summation or two integration,
Mm-hmm.
they often reverse it. But
Mm.
it's not always reversible. So in this
Mm-hmm.
case, instead of first forming
Mm.
utility function and getting to the paradox, I choose earn 1 and I avoid the difficult decision altogether.
Yeah.
Also notice
Mhm.
that but I don't know how to form earn 2. I don't know that all the 10
It's-
11
right.
possibilities are equally
Mhm.
probable.
Okay. Yeah. So there are two things to say about that. So one is it's not clear that earn 2 is actually more difficult than earn 1. So suppose I give you and what people found is if you take decision times as a proxy for computation costs, people are actually faster in earn 2 than earn 1. People, and it makes somewhat of sense, right? So here, well, 50-50 is pretty easy, but I can give you a more difficult computation than this. Whereas here, I don't know if it's red or blue, so I'm just going to toss it up and say it's 0.5 in both cases. Whereas here, if I give you, 0.19 and 0.81, it's not really clear, that I have to compute, So in some senses, EARN2 might actually be simpler, and that's what's been found in several studies so far, that computation in EARN2 actually is faster, or the decision times in EARN2 is faster than EARN1. And also another thing, which I now forget, maybe I will remember it later. Okay, but let me just move on. Yeah, cost of holding two things in your brain at the same time. Okay, so why do we care about the Ellsberg paradox? Oh, okay. The second thing is we have a treatment in the experiment where they don't choose over known probability distribution, unknown probability distributions. We take advantage of endogenous ambiguity. So we give them questions like the temperature. What is the temperature of Tajikistan sometime a year ago, versus the temperature of New York City a year ago? Yeah. So in that case, there's no. So in that case, it's just about how crisp your endogenous prior is, and not over explicit, priors that we give them. And there we control for some of the things that you're talking about. That is, it's not necessarily just about a two-step process versus, say, a one-step process. But anyway, we'll get there. Okay, and the important thing about the Ellsberg paradox is the notion that the distinction between ambiguity in economics, ambiguity is referred to as EARN2. So when you don't know about the probability, uncertainty about probability. And risk is when you're faced with a situation where you know the probability distribution. Okay, so that this distinction generalizes to important economic activities, and the intuition is often echoed that virtually in all real world decisions, your decisions involve uncertain prospects. And so this is Fox and Tversky in '98, and it's basically a very simple sentiment that, except when you go to Vegas and you play parlor games, you don't know the probability distribution. And even when you're playing poker, the probabilities are known. It's just that you might not even know it, right? So to the extent that the probabilities there are varying levels of uncertainty in the world, this could affect many different things. And one of the applications that's been quite prominent in finance is what's called home bias. So this is why do people invest overwhelming proportions of their portfolio in their home countries? And this is a paradox from a risk management and also a portfolio management point of view. That if I'm in Sweden, so Sweden is commonly cited example. If I'm in Sweden, my economy composes about 3% of the world's GDP. So I shouldn't invest in 98% of my portfolio in Sweden. I should be diversified. And in fact, I should even short Swedish stocks, because then I'm hedged against any movement in my income from fluctuations in Sweden. But this is not what people do. People invest, and in fact, Microsoft probably a good example. Many of you might get 401ks or such from Microsoft, and you might invest in Microsoft. Now this is probably a very good strategy for Microsoft, but look at Enron. So when Enron went under, people lost their jobs, and they lost their pension funds or their retirement funds. So there you're looking at when your future and current income are very, very tied together, and so therefore, and by there, you're carrying on too much risk.
You can't explain this by access. It might turn out that for whatever old-fashioned machinery is out there, it's easier to access local stuff.
No, that's definitely true. But this is replicated for institutional investors too. So
and it's the same problem.
It's harder to say that about institutional investors and pension funds, because they manage billions of dollars, and if they don't diversify optimally, nobody in the world should. Because go ahead.
Can I just check what I understood? You said risk is known probability distribution, uncertainty is unknown.
Unknown, right.
And that people prefer risk to uncertainty,
Mm-hmm.
and the home bias is an example.
Home bias is invoked as an example of this. Whether it is or not, that's an open question. But the argument in the home bias example is that people know more about the distribution of returns in the home country stocks than foreign country stocks, right? So then then people prefer to invest in home stocks. Okay. so that's a little bit different. So gambling on your own home team, you might actually get some utility from your home team winning, whereas here, whether Dell does better, I don't really have any pride over that. I mean, but I'm not really American, so, but yeah, so that's been invoked as one explanation, but especially when it comes to institutional investors, it doesn't seem to fly because those people should be agnostic, or they should kind of put aside all sorts of feelings about home teams and whatnot.
So from your point of view, they should be hedging and betting against the home team.
Well.
Because I want utility, I get positive utility of my team.
Well, some of the institutional investors, well, like pension funds are not allowed to hedge, but they definitely should be. I mean, this is a huge imbalance between home stocks and foreign stocks. So I invest something like 90% of my stocks in the home country, and there, I definitely shouldn't invest as much. Whether you should hedge or not, that's a different question. But it's just a magnitude of the problem can't be solved by traditional explanations. Can't be explained by traditional explanations. Okay, so there's several different approaches to explaining the Ellsberg paradox. So the traditional approach has been to relax the axioms. So for example, instead of defining the acts over for any arbitrary act z, you say, if I give you another gamble on z, it's kind of more difficult. But if I give you a certain, so if I add a certain act, so instead of giving you another lottery, if I give you, say, $3 for sure, a degenerate act, basically, then people satisfy the independence axiom. So people have done this, and what you can get is you can get a more general version of subjective expected utility theory. Okay?
I didn't get what is the difference?
So the difference is, so Z in the traditional independence axiom doesn't have a subscript C, and then it can be any act, so it can be any lottery. Whereas here, with the subscript C denotes is that it's only a degenerate act, so it's only acts with probability 1, right? So if I mix two gambles, it's hard to see, and then maybe I'm just confused. But if I give you a certain one, so if I give you a certain one, then people can make these kind of it's easier. At least that's the one of the intuitions for this axiom, that it's easier to make the choice, and now people are people shouldn't violate this. And there you can explain the Ellsberg paradox with these kind of modified versions of SEU. But of course, it is difficult to beat subjective expected utility on both the normative or descriptive level. So for instance, in this case, you can be arbitraged, right? Well, the alternative and the approach that I'm going to be looking at, and my colleagues, is to look directly at the mechanisms that's generating the behavior. So at some level, SEU's normative appeal is very strong. And if you're going to, in Ellsberg paradox, suppose that you asked to design a human being, say, do you want your designed human, so say you're God and you're designing a human, do you want your human to violate independence or not? And there are good reasons to say that you don't want them to violate independence, right? And so by some accident of evolution, maybe, we do violate Ellsberg, or we do violate independence. And so it's worthwhile to look directly here at the mechanisms that's generating the behavior to see if what are the causes that's causing, what are the causal forces behind this violation. And so, so it's also to examine more seriously the question, how do people make decisions? Not just look at how do they make decisions at the outcome level, but what are the components? So basically look inside the machines and see what are the components that's generating their decisions. Okay? And the ultimate goal of this whole approach is to provide new data to discipline and inspire theory. Okay? And the more generally, and here it's probably not going to be as keen to this as most economists, as it's many disputes in economics comes down to debates about the existence of certain perceptual or psychological constructs. So do people distinguish risk between ambiguity? Do people have endowment? Do people have a kink in their utility function? So these are all debates that kind of underlies the central debates in economics these days. It's a very kind of simple assertions about people's utility functions, preferences or utility functions, probability assessments, etc. Okay. So I think I'm running behind on time. So So here's a roadmap. So first I'm going to talk about the tools that we're going to use to look inside the brain. So one part is brain imaging, so that's the sexy part. And I'm going to talk a little bit about the physics, both the physics and the statistics of fMRI. And also I'm going to talk a little bit about these brain damage patients and why we use them. Then we'll get to the rest of the talk. Okay, so the organ that we're interested in is the brain. And so the brain consists of many different particular kind of cells called neurons. Almost everyone knows this. Okay, there are an incredible number of neurons, 10 to the 10th power, and up to 15,000 connections between the neurons. So the scope of the problem is quite large. But fortunately, the brain is modular in design and organized into various cortices, nuclei, sulci, gyri, etc. And so here are some of the different areas. And so people have found, at the first order, many different functions for these regions. Some of them are very well known and very specific, like this strip here is for motor movements. This strip here is for somatosensory, which is say sensing your feelings in your own body, and some places for audition, etc. Okay, so the brain is more or less modular, but it's also very flexible. So you have neural networks that if a brain part is damaged, it can actually come in and supplement some of the tasks. But the first pass, it's modular, and that's where we're going to take advantage of. Okay, so these are some of the 4 traditional measurements of brain activity that we have at our disposal with human beings. One of them, so first one is imaging. So this is typified by fMRI, functional magnetic resonance imaging, which I'll get into in a little bit. So that one is non-invasive. You line the scanner. Eric was in this, so we didn't stick needles or prod him or anything. There's good spatial and temporal resolution compared to some other imaging techniques, which is why we use it so much these days. And fMRI is an indirect measurement of neuronal activity. We'll talk about this later. Okay, there's another technique that we use. It's called the Lesion method. And in this case, it's clearly highly invasive. You're looking at people with brain damage, and we obviously can't go around creating brain damage on people. So we are limited by basically accidents of the world or unfortunate events. And this is very powerful because part of the brain is missing. And so with that, we can assess necessity of a neural structure for behavior. So to the extent that this area of the brain is responsible for a function X, we can see whether it is necessary with lesion patients. There's also neurophysiological recordings. This is mostly commonly done on monkeys. This is when you put electrodes into the organism's brain and record directly the neuronal activity. There are also drug manipulations that you can give people. So there's been some very interesting work done on this, but this study doesn't have any, which is probably good. Okay, I'll skip this slide.
Back to the slide.
Mm-hmm.
What do you think you're talking about?
This is slide. So this is plotted on 2 dimensions: invasiveness and the size of the measurements. So the lesions is measured over years, and it's very macroscopic. fMRI somewhere here, patch clamps and single unit recordings at the neuron level, and with mix in between. So just give you kind of an overview of all of the different tools that's available in the neuroscience area. MEG is so ERP is event-related potentials. These are kind of scalp recordings of your electrical activities. MEG is just a magnetic measure of the magnetic field instead of electrical field.
People like George Orgeman, they actually do artificial real-time lesion vision wake surgery by turning on parts of the brain.
Right, you had
They're not the most accessible subjects, I guess.
Right, right. So actually, in the early studies on motor in very old days, that's how they found the motor cortex. They stimulated a part of the body and said which part of your body felt something. And you say your hand or something. Yeah. So yeah. So but nowadays we pretty much can't do these on normal college students. Okay. So here's the fMRI technique. So this is what happens. So this is a typical fMRI machine that Eric, amongst other people, have gone into. So this is, so you lie down here, and this is the magnet. So there's a donut you get put in there, and we scan your brain while you're making your decisions. Okay, so we get the data from the scanner, and we run into whatever image analysis we want, and we get images like these. I'll go in a little bit more detail in a second. Okay, so fMRI is, as I said, indirect measurement of neuronal activity, and it measures, in fact, blood flow in your brain. So the key to remember is that neuronal activity results in an increase in the level of oxygen consumption due to the increase of metabolic demand. So when your brain does something, it needs energy. And what the brain does is actually it overcompensates and oversupplies blood. And this causes a local increase in the cerebral blood volume. So this is what we see in this cartoon. So in the top panel, on the x-axis is time, on the y-axis is the neuronal activity. So you can see here, there's a spike from the neuron at time 1, and then it goes away. And what's going to happen to the blood flow is it's going to have an initial dip here, very small, and shortly after t equals 1, it's going to be oversupplying blood. So we observe a response as like this, and then it drops down to about baseline around time t equals 10, and there's a slight undershoot that lasts about another 10 seconds for it to go back to normal baseline.
Is the actual mechanism by which metabolic activity turns on more blood flow known?
Yeah, so there's some recent work about how the correlation between the neural activity and the blood flow.
Is it neural, or is it more phase of, what is the actual basis of the mechanism?
For that, I'm not quite sure. Yeah, I'm not quite sure about that, right? Okay, let's see, let me skip that part. Okay, so here's a little bit about the physics of fMRI. How do we get fMRI images? So we need a big magnet for this reason. So in free space, the hydrogen protons in your brain is basically, there's no magnetic field, so it's going to be random all over the place. And what we're going to do is we're going to apply a big magnetic field, and this is going to have the effect of aligning all the protons to the y-axis, right? Okay, resulting magnetization is M, and the way we're going to change things is we are going to apply radio frequency pulse to the magnetic field. So we're going to apply a radio frequency pulse to this vector here, and what's going to happen is it's going to knock it down to being flat. So it's going to knock it. So before it was aligned on Z, now it's going to be aligned on X and Y. Okay. And when you retract when you stop the radio frequency pulse, it's going to come back. So it's spinning here, and it's going to spin back. Okay, and it's going to spin back to around B0 at the Larmor frequency, and it's going to take this trajectory here. So it's going to go whoosh, 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 whoosh. Larmor frequency is just the frequency at which these atoms spin back to Z naught. For any, and there are different Larmor frequencies for different molecule or atoms.
Is that relaxation without heat? Yes,
I'm not.
Is there heating of the brain?
There's no heating of the brain. Sometimes you can get electric or nerve stimulation, mild nerve stimulation, but I don't think that's related to this phenomenon. Yeah. I imagine if there was, there might be a little bit of heat generated, but I imagine if there's a lot, then it wouldn't be safe. Okay. And so what we're measuring, so there are two things that we can possibly measure. So the part of M that's parallel to B naught grows back, and this is MZ here. This is a longitudinal magnetization. There's another part M that's perpendicular to B naught that shrinks. That's MXY. That's here. So as you come back, so as this spins back, obviously this vector shrinks and this vector increases. Okay? And depending on which one of these we measure, well, okay, so one of them is called T1. That's its technical name. It's a relaxation of M back to the alignment with B naught, and T2 is the other one. And what fMRI can take advantage of is that different tissues have different T2 values. They're also going to have different T1 values. It's and that based on the magnetic susceptibility of the tissue, depending on the composition of the tissue, they're going to have different T2 values. And more particular, hemoglobin is diamagnetic when oxygenated and paramagnetic when deoxygenated. And practically, this is going to mean that white matter is going to appear gray and gray matter is going to appear white. Okay, and so this is why we call it blood oxygenation level dependent or bold images.
Why white, gray, white matter? The oxygen.
Yes, it's really just related to oxygen level.
So you're saying that white matter is less vascular, basically?
Right. Yeah. White matter is basically tracts of fiber. Axon fiber.
Different from the regular MRI, which is more limited on the temporal resolution.
This is exactly, so everything I said so far is regular MRI. Yeah. fMRI is just more, it's just kind of more powerful magnets, and which allows you to do this on a functional level. So we can look at blood flow changes over time. So in the regular MRI, it's a static image.
It's very strongly limited by temporal sequence. We do some research at home.
MRI is static. So traditional MRI is static. You look at the knee and just structures, yeah. Well, everything I've said here, there's nothing about fMRI here, but you can extend the traditional fMRI or MRI to fMRI. So you're going to have some. So usually fMRI is very high resolution. So when you extend to fMRI, you make some. There's some cost of having the functional part. So you usually have lower spatial resolution than you almost always have lower spatial resolution than traditional fMRIs or traditional MRIs. Okay, so here's let's see, a quick overview of the steps of statistical analysis of fMRI data. So here you have your image time series, and because you're lying in the scanner, your brains are probably going to move over time. So what we need to do is first we need to realign the brain to a common axis and normalize different people's brains so that we can compare structures. So this is called normalization. There's also a smoothing part, which we apply a Gaussian kernel to the data. This basically is a standard practice to increase the power of the data. Okay, and the traditional measures is traditional analysis is general linear model. There are more sophisticated ways and more exotic ways to do this, but so this is what we're going to stick with here. Then we get these maps that's called statistical parametric maps. So in this case, it's a T-map. So these are thresholded T-maps. So these are like the pictures that you see later on in my results. So these are. This is. The template is being used to align the brain so that so this could be either be single subject or group, but to use group you have to use a template because the people's brains are slightly different, and rotation wise they're also off. Okay, so then we do our standard statistical inferences on these matters. Oh yeah, one thing I want to get on is these are thresholded T-maps. So it's as if this whole picture is a picture of a T statistic, and we've cut off when we pick some p-value at which we threshold the T-map, the T statistic, and we overlaid it on a anatomical brain like so. So this is an overlaid T-map basically. Okay. Okay, so this is another view to really give you the temporal aspect of fMRI. So here, this is one slice of the brain, and it's tracked over time. And we're going to look at the activity in this brain voxel. What was that?
Resolution is
about 2 seconds.
2 seconds.
Yeah. Okay, and so we track the activity in this voxel over time, and we see something like this. So this axis is time, and and here is the intensity. So there you can see this is some kind of a motor or perceptual task, probably a perceptual task. And they see something on the blues, and they don't see something on the reds. So you can see activity increases in the blue blocks, and goes back to baseline on the red blocks. And we run that through our statistical models, and we get a statistical image that looks like this. So this is the raw T-map, and you can see the high thresholds are the brighter spots, and the low activation are the low T statistic are the dark spots. And so you get something like this. So this is an outline of the brain. So this is what you see when it's not overlaid, and it's not very pretty. That's why we overlaid it, and you can't see. It's hard to see which brain areas you're looking at. Okay, so now we're going to look at. That's the fMRI part. So now let me tell you a little bit about the lesion patients. So the lesion patients, you're looking at why. Well, I already said that some of this in the beginning. The point to study the lesion patients is if we took out. To answer a hypothesis of the following, if we took out part X, it would change behavior Y in the following ways. And in this case, you see a very big brain, very big part of the cortex damaged here. But more generally, what we're going to be looking at is very focal lesions. And our patients are all drawn from the University of Iowa Medical School, which has a big database of lesion patients. And they actually fly people in all over the country to do, they do more traditional neuropsychological tests on them, like memory or kind of more simple, like perception.
That doctor right there is missing.
Yeah, so this person has a huge part of their brain missing. Yeah,
They're still alive.
they're still alive. Yeah, you can in fact be missing whole part of your brain, half of your brain, or even more. Then you'll still be actually not just alive but functioning. No. I mean, this is no. This is actually quite. This is quite lateral, so you can't actually see the cingulate there. But judging by the damage, yeah, it's probably missing. The cingulate at least on the whichever side of the brain that is. Okay.
Didn't they say Louis Pasteur had half the brain?
What was that?
Didn't they say Louis Pasteur had half the brain?
I have no idea. I don't know. If he only had half of a brain, then yeah, it's all the more remarkable.
Gets extra points for that, right?
Yeah. Well, imagine if he had his whole brain. Okay, so now we're done with the technical parts, and so let me give you the experimental design and give you the results. So here's a timeline. So what people are going to see, they're going to see a fixation screen, and then they're going to see the trials of different sorts. They're going to make their choice. We're going to give them a feedback of what choice they made for about 2 seconds, and then the whole process repeats itself. Okay? So first they get a fixation screen, which is basically a blank screen with a cross on it. There's no cross on here, but yeah, in this experiment there's a black cross on there. Okay, so the key there is twofold. It allows us to obtain a baseline measure of the brain activity, and also when used between trials, we can allow the brain blood flow response to go back to baseline. And so here's one type of the trial. These are the ambiguous trials. And here you're given the following stimulus. You're told that there are 20 cards of either red or blue. You're not told the composition of the card, and there's a bet associated bet of $10 here. So it's $10 if you pick the correct card, and $0 if not. Alternatively, you can choose $3 for sure. And if you choose $3 for sure, you just get that, and you opt out of the ambiguity, basically. Yeah. Yeah.
That's where it's not going to have the machine is hammering away. They present it to you on your LCD goggles.
That's real. They really get money at the end.
They really get money at the end, yeah.
$43.
Yeah. Yeah. So here, so in these trials, we don't. So then they make a choice, and if they choose red lights up. If they choose 3, this box here lights up. At the end of the experiment, we choose one trial out of this treatment, and we pay them. So we don't give them.
To know the outcome.
No, so it's critical. Well, it's not it's not necessarily critical, but in here we made a conscious decision not to give them the outcome. Because then you learn about how we resolve ambiguity in this case. And also there are income effects that's associated with these type of experiments. Okay, so between we have fixation screens, and then we have the second type of experiment with the risky trials. And here, right, you're told the composition of the deck. You're told that there are 10 reds, 10 blues for $10 or $3. Okay, or $3 for sure. And all of these numbers move around, 20, 10, 10, 10, and by varying them, we can estimate, and depending on their choices, we can estimate parametrically their risk and ambiguity attitudes. Mm-hmm.
Is there always a sure thing?
There's always a sure thing.
So how much money would Eric have won if he got the sure thing?
Yeah, we only pay on one lottery, but there are three treatments. So these numbers are a little bit low, but that's just for exposition. If you chose sure on everyone, I imagine you would come out with like 20-some bucks. Yeah.
Are you going to show the purple one?
Yeah, right.
Get more challenging.
Yeah.
So I didn't understand how only one lottery came.
So you get 48 of these. You get 48 of these trials in the treatment, and we pick one at random at the end of the experiment, and then we paid that one. Yeah.
It seems like with the 6-second choice and the loud noise in LCDs, you're pushing the.
Oh no, this is just an approximation. So yeah. So all of these are, see, the tilde is an approximation. It's free response. It's self-paced. Yeah. On average, people take about 6 to 8 seconds to make these choices. Okay, so here's the second type of trials. So here we're taking advantage of kind of the internal uncertainty of people. So in the ambiguous, we asked that high temperature Dushanbe, Tajikistan on November 7, 2003 is above 50 degrees Fahrenheit. And you are to choose yes or no, okay? Or you get $10 for sure or $3, okay? And the other one for the risk is high temperature New York City, New York on November 7, 2003 is above 50 degrees Fahrenheit, yes or no. So as you can see, and this has actually been done by other people, namely Tversky and his co-authors, to kind of go beyond the Ellsberg type urns. And here you really have a much better control of the missing, the missing information is endogenous. And also it's very, and the Ellsberg paradox will be preserved if you're indifferent between yes or no in the New York City, between yes or no in Dushanbe, Tajikistan, but you prefer New York City to Dushanbe. And these effects are, in general, at least in the literature, they have been larger than the effects in the Ellsberg urn. Just because.
So everybody choose this one, but then $3, because even if you don't have any knowledge, random choice, you get $5.
Well, but it's the same thing here, right? Yeah. So I mean, these conceptually, you can make a very strong case that these are all the same. But in terms of actual people, and their knowledge, it's yeah. Okay, and the informed opponents. Let me just skip that one because I only have half an hour left. Okay, so here's a preview of the results. So what we find is that there exists brain areas that's correlated with the expected dollar value of people's choices. Okay, so there's a part of the brain, the activity in that part of the brain is correlated with expected value. So when people make a choice with high expected value, their blood flow increases, quite a bit. And when they make a choice with low expected value, it goes up by not as much.
That's just expectation.
These are all expected dollar value. Yeah.
I think that you find that it's actually a clear function that region, the actual intensity of the flows are correlated, and therefore, assumedly, neural activity correlates with expectation, expected value, return.
Right. Not just returns or yeah. Well, in the ambiguous case, it's hard to say because expected return is just we assume that the probability in the ambiguous case is 0.5. So there you have a confound between the actual value and the expected value.
So people have explained before with in monkey models expectation of where to look and so on to find areas that are expected value.
Yeah.
This is the first result on.
No, this is not the first result. This has actually been known that monkeys and humans, their brain areas that's it responds to expected value. Yeah, but it's we find that here, and also there's another result. It's this line basically. That's the new result. So the brain, there's another brain area that signals level of uncertainty. So high level uncertainty here is ambiguity, and low level uncertainty is risk.
So is that again the amount of blood flow in that area is proportional to the level of uncertainty?
We only have 2 levels of uncertainty. Yeah, there are studies now that varies the level of uncertainty by varying the coverage.
High blood flow versus low blood
Blood flow, exactly. Yeah. Okay, and so here's a new result that the activity in the expected value region is lower under ambiguity than risk. And this is interesting for 2 reasons. That, well, first of all, nobody's found this because, well, there are 2 studies on ambiguity, but nobody's found this. And also, it says it suggests something that's very interesting, that we're actually measuring not just expected value, but expected utility, right? Because people prefer the risky choices to ambiguous choices. So under any kind of expected utility theory, the expected utility for risk has to be greater than ambiguity. So this is exactly what we find here, and this is a very strong result. There's only one region in the brain for this is true for both this and this. Okay.
I'm sorry, let's try. Can you give me just a simple example of the difference between ambiguity and risk?
In the last slide. Here. Ambiguity is when they see this trial. Risk is when they see this trial.
But you say some people educated.
Mm-hmm.
Because they're identical.
So some people we don't know whether they look at identical. Some people make the same choices under both, so they're consistent. And it's an open question whether they're actually identical or not. And there's a lot of talk about, and it's one clue is that people who are identical here, such as yourself, are ambiguity averse here. So yeah.
You confirm that I was with that one.
Yeah. Actually, everybody was ambiguity averse in that one. Yeah.
So here you're using the word ambiguity, where earlier you used the word uncertainty.
So uncertainty I'm using here as a general term that embraces both ambiguity and risk. Yeah. In the literature, in the decision theory literature, the terminology has been very confusing. So some people call it uncertain. Some people call Knight in the 20s called basically ambiguity uncertainty, and risk is just risk. And Ellsberg in the 60s came along and defined that as ambiguity and risk. So most people use ambiguity, and so I mean there are only so many words in the English language. So I chose uncertainty to be kind of the overarching term.
Can you the last point there? No, go back forward. The last bullet.
Which one? This one?
No.
Oh, the activity in the.
The activity and expected value regions identified above.
Right.
Is lower when there's more.
When people are making choices under ambiguity versus risk.
So you're saying and they made a comment that meant that we had a better, more accurately reflecting expected utility than expected value.
Well, we don't know, but that's definitely suggestive that we're measuring expected utility rather than just expected value. I mean, the subtleties are very.
The brain area is expected utility rather than.
Exactly. Yeah. Yeah. Okay. Right. Yeah. Sorry. Yeah. The terminology. Okay.
Then there's another question. Your third point said that the brain area does not correlate with the expected dollar value, it correlates with this expected other thing. Next question, is there a brain area which does correlate with the expected dollar value?
Oh, I see. Okay. So the problem, it's very subtle, right? So usually expected utility, or utility function, is some function of the value. So your utility function is normally assumed to be somewhat concave of the value. So the differences are very subtle, and expected value and expected utility are highly correlated, in most of the studies. So it's really hard to, I mean, it's almost, I would say it's very difficult to separate expected value and to find a region that's correlated with expected value, but not expected utility, and vice versa. It's, yeah. So that's part of the challenge in this.
Areas occur in the cognition part of the brain, or?
This area is in a very primitive part of the brain that basically rats and insects, or reptiles definitely have. Not sure about insects. This part of the brain is more of a novel part of the brain.
Cortex?
Well, it's in the orbital frontal cortex, but it's quite old. It's it's an extension of the limbic cortex, but we'll get into that in a little bit. Okay, so the other part of the finding is that if people don't have the brain area that we hypothesize to be signaling uncertainty, then we don't see ambiguity aversion. And this is, this lends to lots of jokes that, the brain damage patients are actually more rational than your normal Caltech students or anybody else in the world. And surprisingly, we also don't see risk aversion either. This is a big deal from the point of theory, because most models of ambiguity aversion are agnostic about the links between ambiguity and risk. Okay, so let me show you. Just the pictures. Okay. Yeah, but there's lots of different data. Yeah, there's lots of different. Yeah, I mean, I'm just getting to the imaging part. There's a lesion patient too. Okay, so this is let's see. Okay, so this is a part of the portion where the null hypothesis here is that the brain activity doesn't correlate with the expected value operator here. Okay. So beta amb in this case measures the baseline effect of ambiguity. Beta risk measures the baseline level of risk. The gamma measures the correlation between the effects of expectation on the brain activity. Pi is a vector of nuisance parameters, and this is random effects in the pooled over 16 subjects.
Who gave you that little model?
You mean this one?
Yeah.
Well, this is yeah. Well, we just use it.
Model.
Yeah, this is your standard mixed effects model. Well, this is a random effects model, so there should be like little eyes here and etc. But it's just notation, and it just kind of makes it hard to see. Okay, so this is the region for which we reject the null that brain areas are not correlated with the expected value, and so this is a striatum here. More generally, this is more specifically, this is what's called the caudate nucleus, and this is a very old part of the brain that basically, monkeys, or definitely monkeys, but also reptiles would have. And this region has been known to be correlated with expected reward of many different sort, anticipated reward, expected reward. Let's see, what else should I say about that? Yeah, so this is a template. Oh no, this is kind of a standard template that comes with the what's called the Montreal Neurological Institute template. It's an average over 200 subjects almost, and so that's why it's kind of blurred. Yeah. Okay, there's another region that's reacting to uncertainty. Here we're comparing just the baseline measures of ambiguity versus the baseline measures of risk. And we're looking for areas where the activity under ambiguity is significantly greater than the activities under risk. And one of the areas we find specifically is here in the orbital frontal cortex. So the orbital frontal cortex is kind of laying along your orbit bone. That's where the name comes from. And even though it's in the frontal cortex, it's actually quite an old part of the brain. It's part of the limbic structure of the brain. So the location actually is quite deceptive, but it's definitely a more older part of the brain than kind of than say like this part here. And one thing to note is that this region doesn't correlate with expected reward. So here is the activation that you see from this area. So this is sort of what you saw in the cartoon, except it's not nearly as nice because this is actual data. So blue is ambiguity, green is risk. As you can see here, blue is above green. You can see it clearer. Blue is above green in this area. And time 0 is the onset of the trial. So when people see the trial, as soon as people see this, the orbital frontal cortex is activated. And let's see, right, and here's the mean decision time. So people's choices are self-paced. So it takes on average for them about 6 seconds to make the choice. So it dies down around this time. Let me give you the different one. So this is the striatal activity, and you can see kind of a different, the opposite pattern. Here, risk is greater than ambiguity, so green is above blue, but also the time at which activity occurs is quite a bit later. So instead of occurring at time 0, it basically occurs probably a few seconds before people make the choice.
Those are extraordinarily clean results. Did you expect such a clear result from the data, and that people got such clear answers from those people?
So people have gotten data like this from these kind of subtractions. And people have found that, the correlation, so one thing to note is that the correlation between, the correlation between expected reward and brain activity has been known for at least 2 or 3 years. And so that is the more technically difficult part to find, that you want correlation between some variable, some abstract variable that we present to them. So the technical parts are, so to answer your question, it's not more clean than, it's in the past 2 or 3 years, it's been quite feasible to do this type of, to find these kind of correlations. Okay, so let me compare the 2 regions and also give you a hypothesis for what's happening. Okay, so here is the activity for the OFC, and here is the activity for the striatum. So one thing to note is that the peaks are early and late, and it's switched, right? So you have ambiguity greater than risk for OFC, and risk greater than ambiguity for striatum. And the obvious hypothesis is that OFC sends a signal to the striatum that signals, for whatever reason, that there's a uncertainty in the problem. So let's see. Okay, and to test that, that's where we needed the lesion patients. So we needed a question to say very clearly, is the OFC necessary for this for ambiguity aversion? And more generally, and also the connections between the OFC and the striatum are quite well known. So if there is such a circuit, we know that there are actually physical circuits, physical connections that would be able to support it. Okay, so for the lesion patients, we separated people into 2 different groups. Those with orbital frontal lesions, so that's people with lesions overlapping with one of these areas. And we also have control lesion patients. These are patients with one of lesions to the temporal cortex that's here. That's not that doesn't contain that's not activated basically in any of our contrasts. And the groups are matched on measures like IQ, age, memory, and the cause of lesion. And the cause of lesions are all neurosurgical lesions from epilepsy or brain tumors. And in fact, the patients that we have have a higher mean IQ than the population. So the average is about 107 with a standard deviation about 6 or 7. So it's actually a little bit smarter than your average in the average population. So this is another clue that's actually quite remarkable, that people with damage to two groups of people with damage to this area doesn't affect their IQ, or at least not appreciably.
And you meant lesion on either side or both sides?
In this case, it's either side. Most of them have been on the right side. In the lesion experiment design, we have a simplified version of the Ellsberg task. So subjects are presented with 2 different decks. There are the risky decks that has 100 cards, 50 which are red, 50 which are blue, and the ambiguous decks, 100 cards, and they don't know the composition of red or blue, but you know that there are only red or blue available. And people chose between gambles for $100 or 100 points with risky or ambiguous, from the risky or ambiguous deck, and a certain payoff. So certain payoffs range from 15, 25, 30, 40, or 60 points. Oops. So here is the summary of the behavioral data. So these are the control lesion patients. We present them with an ambiguous deck for 100 points, and we ask them, would you rather take the bet or take the certain amount, 15 points, right? Or 25, 30, 40. And what we see is that 29% of the population, or which is like 1/7, chose 15 for sure. 29% chose 25, 50% chose 30, and 71% chose 41, and etc. Okay. Now compare that with the risky deck. Now what we see is that 0% chose 15, 14% chose 25, and etc. Okay, so what we can see two things from here. That people are somewhat risk averse in that their cut point, so a expected value maximizer would choose to take the gamble on 15, 25, 30, 40, and choose a certain in only 60. And we see that people are slightly risk averse, but they're definitely ambiguity averse. So they are more willing to take the certain outcome in ambiguity than risk. Now compare that with the orbital frontal patients. So there, nobody chose 15, 25, or 30 in either risk or ambiguity, and only 20% chose 40, and only 60% even chose 60. So there are some people who are clearly risk preferring. Okay, so the 2 points again are that choices are not random. So these are not people who don't respond to incentives. And also the crucial difference that we can see by just eyeballing the data is that the orbital frontal group is less ambiguity and risk averse than the control group. So to make that more concrete, we estimated people's risk and ambiguity attitudes with the stochastic choice model. And we had to assume parametric forms because we don't have a lot of data here. And we pooled the data for the group, so we're looking at group differences. We estimated via maximum likelihood, and we used a bootstrap to obtain confidence intervals, and especially to look for bias and robustness in the data. Okay, so the utility, so we assume the utility function to be a power utility function, so x to the rho. So rho here is going to measure risk aversion. Ambiguity aversion is going to be measured by this function here, pi, and it's also a power function, p to the pi. What's significant about this is pi for the gamma, not pi. Gamma for the risk treatment is going to be constrained to 1. So people are assumed to weigh probabilities linearly in the risk case. And the ambiguous case, in all the ambiguous probabilities, we're going to assume to be 0.5 because these are all binary choices. So what's essentially going to be is that we're going to raise 0.5 to the gamma power. And so the underweighing or overweighing of probabilities is going to correspond to either ambiguity aversion or ambiguity preferring or ambiguity aversion. The utility function is quite standard. They're going to combine probabilities and utilities multiplicatively. We throw that into a logit model and estimate it with maximum likelihood. And what we can do is the following two-dimensional interval analysis, confidence interval analysis. So we plot gammas we plot the gamma on the x-axis. So here is ambiguity preference, and we're going to plot risk attitudes on the y-axis. And this is going to demarcate the 4 quadrants into zones which people are ambiguity preferring or risk preferring. The thick dots, the thick symbols are the maximum likelihood estimates. The small dots are bootstrapped pseudo-sample estimates, and the ovals are the 90% confidence intervals. The tilt of the ovals is going to be the correlation between the ambiguity parameter and the risk parameter. Okay, so this graph says a lot, actually. Okay, so the orbital frontal lesion patients, what we can see is what our intuition basically tells us is slightly ambiguity preferring and slightly risk preferring, but the 90% confidence interval encompasses the ambiguity neutral and risk neutral point. whereas this can be rejected for the control lesion patients. So the control lesion patients are ambiguity averse and risk averse. And also remember this point, gamma equals 0.82 for the orbitofrontal lesions. So this is the maximum likelihood estimate for the ambiguity attitudes of the orbitofrontal lesion patients. Okay, so this slide is to link the neural, the behavioral, and the lesion data. So with new techniques like this, with fMRI and lesion patients even, what we want to know is really, can we use our existing knowledge? How does it fit well with our existing knowledge and can take us beyond, right? So we wanted to fit our existing knowledge, and we want to tell something extra. So this is what we attempted to do. So we take the contrast values from the brain imaging data in the right orbital frontal cortex. So this is the difference in the brain activity between ambiguity and risk. So this is the extra activity that the brain experiences under ambiguity than risk, okay? And we're going to take that as our brain proxy for people's ambiguity attitudes, okay? From behavioral choice data, we can feed that through our stochastic choice model and estimate the ambiguity preference parameter behaviorally. So this is the traditional experimental behavioral economics, or experimental economics, behavioral economics paradigm to estimate people's preferences from their behavior. This is individual data, so each data point represents the ambiguity attitudes of individual, and what we see is a modest but significant correlation between the two. The correlation is 0.55. And what's significant about this is that not just the correlation, but also we can use this regression as a model for out of sample fitting. In the specific case here, we can extrapolate this regression line to this point here. The contrast point is 0. So the significance about this point is, think about your lesion patient and think about what the difference between ambiguity and risk in their part of the brain. So by definition, it's 0 because they don't have that area. So there's no contrast and there's no activity in either contrast. And so this is the imputed value, and which is 0.85. And remember our estimate from the lesion attitudes, or the ambiguity attitudes, is 0.82, which is basically about as well as you could ever hope for in studies like this, with lots of noise in the process. Okay, so some conclusions. So one is just that the redeeming feature that we can distinguish between ambiguity and risk at a neurobiological level. And an open question is whether we're observing lowered expected utility in the ambiguous case. And if that's the case, then that would go directly to the heart of, are we observing economic variables? And if we can observe utility, then that alone is worth doing for the next 20 years. Okay, and also data reveals something that's not predicted by theory. And so specifically risk and ambiguity aversion share a part of the brain. Most models of ambiguity aversion, as I've said, is agnostic about this part. And an open question is whether people approach risk and ambiguity with a uniform apparatus. Okay, evolutionarily speaking, there's no reason why we have two parts of the brain, one devoted for risk, one devoted for ambiguity. It just doesn't make much sense. And finally, ambiguity aversion may be an epiphenomenon, so it may be just an adaptation and that's just kind of a product of some other process that's going on in the brain. One thing to note about these lesion patients, they may look like, they look ambiguity neutral, so they actually obey subjective expected utility theory better than we do. One thing to note is that these patients are frequently financially destitute after several years after they acquired their lesion, and that's been one of the puzzles about these patients, that they're high functioning, high IQ, but they just seem to make bad decisions. And in neuroscience, neuropsychologists have looked for 10, 20 years for what specific deficits do these people have. And one of the deficits they found, in addition to, in this case, you saw that they're ambiguity neutral, is that these people don't seem to learn as well as normal people. They don't seem to integrate consequences. And this is kind of very hand-wavy at this point. They don't seem to integrate the consequences into their decision-making. They don't seem to learn like normal people do. And this is a very strong clue about maybe that ambiguity version is part of the brain that's devoted to learning of some sort. And so ambiguity version is just a product, epiphenomenon, of how the brain implements decision-making and learning. Okay, so but that's very speculative. Okay, what happened? Okay, so these are some people who are integral in helping us with the in our paper. Steve Quartz, Peter Bosars, both professors at Caltech, Cedric Anand and Shrish Mysore are graduate students, and Steve Flaherty and Mike Tishka are technicians that helped us with the imaging. Okay. And it was in December 9th issue of Science. And that's it.
So how did you correct the bias of those patients' previous behavior before they got this problem?
Right. So part of
You have to correct that. Otherwise, whether you show,
well, we don't.
of the two.
That's why we needed both the orbital frontal patients and the control lesion patients. That we're looking at the differences between groups. That it would be very nice.
Yeah. Before they have this, they may have.
No, so right. That's why the control for the causal lesions was very important. That the orbital frontal patients, there weren't motorcycle riding people who acquired their damage through fall or some sort. Yeah, but it would be very nice to be able to have before lesion and after lesion. But it's just that they don't come in. They're not going to come into your institute until they acquire the lesion.
So, I have a comment on that last comment about the ambiguity talk. So, it seems a very fundamental, potentially evolutionarily sculpted part of our behavior and thinking. The question would be on value information. When do I put effort in to look and either learn about the long-term or short-term aspects of the world? Something that's obviously ambiguous presents that opportunity to actually probe it.
Right.
And so the whole notion of pausing to gather evidence before acting, which is a whole big structure and a whole big behavioral constellation. So I would hope or think and hope that there might be some link between opportunity for evidence gathering and this ambiguity signal that's linked together somehow behaviorally. And maybe what you're seeing is people that, not that they don't learn, they never orient themselves to trying to understand.
Right. I mean that's the right. So that's one clue, that if you give people on a repeated, if people get to sample the ambiguous urn repeatedly, they should prefer the ambiguous urn to the risky urn, and they do. So the problem, when they see it's just a one-shot game, why is it that all of a sudden they don't prefer the ambiguous urn? So yeah, I mean that's kind of, it makes sense that to embed it in a kind of a more repeated game structure, but it doesn't at least it doesn't jump out to why people would prefer risk to ambiguity in a one-shot setting.
I don't understand the comment about when you get repeated trials on the ambiguous.
Okay, so the
What if the evidence is that it's real shitty?
Oh, it can be really bad, right? So if the probabilities are 50-50, that's the worst you can do. If it's right, you get a choice between the red and the blues. So yeah.
So can you comment on differences between the card or burn game and the word game? And differences you saw between
Right. So we saw. Yeah, so I mean, there are several kind of interesting differences, and we didn't report. We kind of briefly talked about in the paper. One difference is in the lateralization of the activations in the expected utility portion of the brain. That people that the card decks activated the right brain, the right striatum more than the left striatum, and it's vice versa for the knowledge case. But that's been so.
The language.
Yeah, so language activates.
Right
left. And it basically fits in our traditional notions that left part of the brain is language, right part of the brain is abstract. And there it's reflected in the expected reward region as well. And that's quite interesting. And I'm not sure I've seen that result at least explicitly reported in many papers before. Another part is that
How about that correlated to the size of the ambiguity inversion?
So there,
larger effect.
right,
Ambiguity
yeah.
or
Behaviorally, we do see that people are more ambiguity versed with the word problems than the card decks. In terms of correlating the behavior and there we don't see a very strong link between the two. Yeah. And it might be noise, it might be some other issues, and we don't really know.
So for people like myself, so Ming reported over the top this morning that even with all my training, I showed the ambiguity effect with the language structures. I'm thinking that it could be the fact that that's kind of a more natural effect, and when I saw an abstract rendition.
Yeah, exactly.
Oh yeah, I know this.
Right.
I know this. This is like this is 0.5.
Yeah.
But with the language, I wasn't thinking that way. So it could have got something in a more natural state.
Right.
without the education.
No, Caltech subjects, and you might be able to test this. Caltech subjects students are famously expected or famously risk neutral. But what they see the experiments as basically ways of extracting money from experimenters, and they're willing to go extraordinary lengths to do that.
We always defected it.
Oh, really? I heard anecdotally Caltech subjects cooperated much more.
Most people cooperate.
Yeah.
You always get confused.
Yeah, right.
Like I always.
Yeah.
I knew everyone would cooperate because they knew
Yeah.
that.
Yeah. No, optimal strategy. The socially optimal strategy is to cooperate, but the individual rational strategy is to defect. Yeah, but Caltech subjects are kind of famed for doing things that are that make the most money for them, even when it's kind of socially, even when it's very difficult to coordinate socially, they somehow manage to do it, and partly because it's a small community. But in this case, there's no social part going on at all.
Anything else? Thanks very much.
Yeah.